Okay, here's the CET236 Homework 5 Superposition question 3. And again, we've got two independent sources, Vs and I1, but now we also have a dependent source, I2, right? And remember, for dependent sources, we can't replace those. So in this case, we can only generate two subproblems, not three subproblems. There are three sources, but only two of them are independent sources. So let's see what that does to how we solve the problem. Right, so the first one is what happens, what's the effect of Vs? So there's a, Vs has a plus at the bottom and a minus at the top. And then there's our I2. And if we're getting rid of I1, then that means it's just an open circuit. So all we've got is R1, which is for 4K, and R2, which is 20K. Okay, ohms. Okay, and Vs is 24 volts, and I2 is 3.4 times Ix, and Ix is defined there. Okay, so how do we do this one? Well, because we've got one current source on the outside, I'm very tempted to define a mesh there, and let's go with the mesh in that direction. Let's call that one I1, and then the I1 equation for the mesh is going to be 20,000 I1 plus 4,000 times I1 plus I2, because they're both going in the same direction, minus 24 equals 0. Okay, so what's that? That's 24,000 I1 plus 4,000 I2 equals 24. So that's that one. And then the I2 equation is our freebie, right? Because we just get that I2 equals 3.4 times Ix. I2 is 3.4 times Ix, and we can think about the KCL equation. It says that I2 plus I1 equals Ix. Right, so you can rewrite this to say Ix equals 1 on 3.4 I2. So that's 1 minus 1 on 3.4 times I2 plus I1 equals 0. Now we have two equations in two unknowns, and we can probably plug those quite happily into MATLAB. Let me just format things a bit better over here. Right, so now we've got, what's our A matrix? Our A matrix is going to be 24,000 and 4,000. And then on the other side, the I1 is 1, and the I2 is 1 minus 1 on 3.4. And then the B vector is 24 and 0. So then our Q3 ands through 3 currents equal RFAB. And this is version 1 of them. And let's see if that runs. Right, so we've got our I2 is minus 1.855 milliamps. Right, so I2 equals minus 1.855 milliamps, and the thing we're after is the voltage across the 20k. So V out 1 is going to be 20,000 times 1.855 milliamps. Right, so V out 1 equals Q3 currents 1, and that's going to be, we want I2, so that's, sorry, we want I1. We don't want I2, we want I1. So I1 is 1.309. Ah, I have a problem. I see what the problem is. So, yes, let me just correct that. Right, so it's not I2 that we need to use to get V out. It is I1. Right, because I1 is the thing that's going here. The trouble is, our V out, our I1 polarity is like this, but our actual V out polarity is like this, right? So our current is 1.309 milliamps is our I1. And then our output voltage is 1.309, is actually minus 1.309 milliamps times 20,000. Right, so that's where we get into a bit of trouble. So our V out is going to be 2,3 and times 20,000, and it's got to be, no, it's got to be 1,3. Yeah, and it's got to be negative because I took my I1 going in the wrong direction. Right, I can do that. I just need to know that the polarity of my mesh for I1 is different from the polarity of the output voltage. Right, and if I do that, I get a V out 1 of minus 26.18, which is what I got here, so that's good there. And then I need to redo the analysis for right, so that's minus 26.18 volts. And then I need to redo the analysis by replacing Vs with its ideal, which is just a wire. So then I get, well, what do I get? I get, that's a bit thick. I got the wrong one. I want a pen. So let's just erase that. Let's go back with the pen. We'll go to blue. Right, so we have our dependent current source, and we have R2, and this time we're replacing Vs with a wire, and then we're keeping I1. Okay, and there's I2. R1 is our 4K, and R2 is our 20K. And this time we still need to get the voltage source there. So now let's think about this one. This one's a little trickier, right? Because we've got three meshes. Let's see if we can do it with three meshes. This time, however, I'm going to take this one going in the right direction so we don't get confused with polarities. And I'm going to make that one go around like that, so that's an I2. Yeah, see, so I don't know whether we can do mesh analysis easily with this one, because we've got two current sources. And remember, with mesh analysis, we don't want to do KVL, right, Kirchhoff's voltage law, because we don't know what the voltage drop across the current sources is. So let's have a think about how we could do it. Oh, it's not too bad, right? So let's just define I3, right? We'll define our, now this I2 is different from this I2. I probably should have done IA, IB and IC. So why don't we do that? Let's just make that one IA for mesh A. This one's B. And the purple one is C. Right? And we get a freebie, right? Because I2 equals IC. So that's all right. And then what we can do is we can define a super mesh. Maybe, if we can get the right color. Thought I selected a color, I didn't. Now we can define a super mesh that goes around like that. Right, so we get the super mesh, and so the super KVL, we get 4000 IB and minus IC, right, because the purple one's going in the opposite direction. And then plus 20,000 IA equals 0. And then the purple one, let's go back to purple. Right, the purple one has IC equals I2, which is equal to 3.4 IX. And remember, our IX is this current. Okay, so let's just continue with the way we did the other one, right? So that means we can say that Ix equals 1 on 3.4 times I2, right? And then we get what do we get? Ix is also equal to IC minus IB. So we know IC equals I2, and that's 3.4 Ix, and Ix is IC minus IB, so we get IC equals 3.4 times IC minus IB, right, which means that we get minus 2.4 IC plus 3.4 IB equals 0. There's another equation. And then we need 3, right? Because we've got 3 equations. So we've got 3 unknowns, so we need 3 equations. So I think the third one we've got to look at is what happens in this branch, right? Because we've got I1 is 14 milliamps. So we've got, let's just try another color. We'll go with red maybe. Right, so we've got I1 equals IB minus IA, and that equals 14 milliamps. Okay, so now we can probably write a matrix equation. Let's go with, I don't know, is there another color we could use? Maybe a darker purple. Right, so that means here we've got nothing for IA, so it's just, oh no, there it is, there's IA there. So that super KVL is 20,000 and then 4,000 for IB and minus 4,000 for IC. And then this equation, right, we have 0 IA, we've got 3.4 IB, and we've got minus 2.4 IC, and then here we've got minus 1, 1, 0, and this is IA, IB, IC, and the constants we've got for each of them are 0, 0, and 14 by 10 to the minus 3 by the looks of things. So let's see if we can put that into MATLAB. Okay, so this time we get A equals, it's a 3 by 3 matrix, so 20,000, 4,000, minus 4,000, 0, 3.4 minus 2.4, and minus 1, 1, 0 as our A, and our B matrix, B vector is 0, 0, 14, well, let's just do it, 0.014 milliamps. And then our currents 2 is just that. Let's see if that runs. And the one we want is IA, so it's 1.273 milliamps. Right, so our V out 2 is going to be 20,000. Now, because we've got the polarity right with the current through the 20k resistor this time, we don't need to negate it. So it's going to be Q3 currents 2, and we want IA, which is going to be 1,3. And let's see what that gives us. Ooh, that's not quite right. No, it's not going to be 1,3. It's going to be 1,4, isn't it? Because it was a 3 by 3. So it's 25.45. Let's just see that that was the right number. Where's it gone? There we go. 25.45. Okay, and then the total V out is just the sum of those two values. And that's what we get. Okay, let me just paste that. Right, so our V out equals VO1 plus VO2, and it's 0.7273. And I'll try and put that all of those MATLAB things